Hi, this is a screencast on rotation and circular motion, where the topics of uniform circular motion, rotational kinematics, and some things involving torque will be discussed. For uniform circular motion, it's really just described as the motion of an object traveling in a circular path as constant. The period of motion is the time it takes to make one full rotation. It would be the time it takes you to go from this point on the circle all around the circle and back to where it came. And so then frequency is the reciprocal. F, the lowercase f, is equal to 1 over t, which is period. And what it is then is the amount of cycles per unit of time. Usually for revolutions per second is hertz. Explaining tangential velocity is just perpendicular to the radius of the circle. Wherever that velocity is pointed, whatever velocity it's going, if the connection breaks, like here, the object will fly in that direction. So mathematically, tangential velocity is 2 pi r over period. And then centripetal acceleration, as you see in the top right, towards the center, and that's the acceleration of the object in circular motion is towards the center. And then centripetal acceleration, there's a bunch of ways to look at it, but a lot of people simplest to do t squared over radius. And so then you get into centripetal force, and centripetal force, Fc equals MAC, is very similar to translational motions, F equals M times A. Because in this situation, an Fc really acts as the net force. The net force will always be towards the center. That's how it works. This is a basic example of a uniform circular motion problem. And so the question is, roller coaster with passengers is a mass of 2,000 kilograms, and the radius of the curvature of the track at the bottom of the dip is 24 meters. It has a speed of 18 meters per second at this point. What force is exerted on the vehicle by this track? And so what it gives you is it gives you M. So M is equal to 2,000 kilograms. And then it gives you VT, which is 18 meters per second, so you don't have to find that. And you know R in this situation is equal to 24 meters. And so if you look at the photo on the right, it'll help you understand the forces involved. And so the speed is the tangential velocity, and then and it's asking for the normal force, which is here. It's asking for what force is keeping the roller coaster from going into the track and bad things happening. And so all you have to do is use some of the universal circular motion equations. F net in this equation is Fc. And Fc, there's only two forces involved that we know of. That's Fn minus Fg, because Fg is always negative, and you can write it like that most of the time. So you want Fn. Fn is what you want. And so then all you're really finding is Fc plus the force gravity. And so all you have to do is plug those equations in. And so Fc is equal to M times AC. And if you really want to simplify it, you know AC is equal to V squared over R. So Fc could be equal to M times Vt squared over R. And so then all you have to do is plug everything in. And remember that force gravity is mg, so it's 2,000 kilograms times 9.8 meters per second squared. So you plug everything in and solve for Fm. And that's all you have to do for that. And so you get Fm is equal to 46,600 newtons. And so since it's multiple choice, rounded, and you get B, as was already underlined. Is rotational kinematics. And really the charts in the front here in the middle really show you what rotational kinematics is. It's just like linear kinematics, but with angles, basically. And so all the equations for rotational kinematics have analogs and counterparts on linear rotational kinematics. Then we get into the real forces involved, which is torque. So rotational inertia is you've seen this symbol over here, I. I is rotational inertia, and what it is the resistance to rotation. Rotation is important, and so torque that is positive is going to be actually counterclockwise, and then negative torque is clockwise. So it can be a little confusing, but you got to keep that in mind. And that's important when you're talking about concepts like net torque is equal to moment of inertia times angular acceleration. And so that means that if net torque equals 0, alpha will equal 0. And so this is a simple example of a rotational kinematics problem. And so the question is saying you have a cylindrical space colony, so it's a cylinder, make that clear, and it has an 8 kilometer diameter, so a 4 kilometer radius, and it's 30 kilometers long, and it's been proposed as living quarters for people in space, has things inside, and has to be held in place by the rotation of the cylinder about the long axis. How fast will such a cylinder have to rotate to produce a 1g gravitational field at the walls of the cylinder? Keep in mind that we already have the answer circled, but you need to keep in mind that the units are radians per second. So it's asking for that in terms of angular velocity. So you're looking for omega. And so, but now it's giving you your radius, and so that's what you care about, and it's 4 kilometers. That's what we're taking from it. And that you also know that acceleration is equal to gravity, and that equals 9.8 meters per second squared. And now you know, and what you know that AC is equal to V squared over R. So that's all you have to use here. So you plug everything in, and so for V, and V is equal to 197.99 meters. Now what you also know is that V is equal to R times omega, and so V over R equals angular velocity. And so all I have to do is plug all that in and solve, and you get 0.49 radians per second, and that is a 0.5 radians per second. The final problem we have here is number 8, and so the problem reads, a wheel has a radius of 0.25 meters, so that means that R is equal to 0.25, and its initial velocity, VO, is equal to 43 meters per second. And then it rolls to a stop, so it's VF equals 0 after 225 meters. And so first it's asking for the linear acceleration, then it's angular acceleration, and then it says the wheel's rotational inertia is 0.155 kilograms a meter squared, and it wants the torque exerted by friction on the wheel. And so what we do is we start off by remembering from translational kinematics that Vf squared is equal to Vo squared plus 2a times displacement. And so that in this scenario you have both Va and Vo, and you have d, and all you have to do is solve for a, and a equals to negative 4.1 meters per second. So just plug everything in and solve for it. And then it's asking for angular acceleration. And you know that A is equal to omega, angular acceleration, times R. And you have R and you have A, so all you have to do is solve for it. Let everything is solve, and you get negative 16.43 radians per second squared. And then it's asking for the torque exerted by the rolling friction on the wheel. And so we know that net torque isn't equal to 0 because it's moving. And you know that there's only one source of torque, and that's going to be friction. And so you know that torque is equal to torque is equal to moment inertia times alpha, angular acceleration. And you know both I and you know alpha, and so you plug it in and solve for torque, and you get negative 2.55 newtons times meters, and you get, and that's what you get. So this is a good example of a simple rotational kinematics, universal circular motion, and torque problem. Thank you for watching.